I'm Professor Len Kelly. This is Math 325, Linear Regression 1. And today I want to explore our simple linear regression model using matrix notation. We're going to look at an example that we have already dealt with and make the connection between those results and the results that we would obtain using matrix algebra. The simple linear regression model, as we know, can be written as yi equal beta 0 plus beta 1 times xi plus this random error term epsilon sub I. And we can write that in matrix notation as you see on this particular slide. Now it's important to recognize the matrix X has this first column of 1s. Convince yourself that if we take the matrix X times the column vector beta in this case, we have to have that column of 1s in order to capture the beta 0 or the intercept term in our model. Going back to the model, you can see that we have to have that intercept term beta 0, and to get that intercept term we must have this column of 1s in our data matrix associated with our regressor variable x. Our goal, as we stated before when we first introduced simple linear regression, is to minimize the sums of squares error. The sums of squares error in this case can be written as the sum of the residuals squared. And if we want to find the sums of the residual squares using matrix notation, we're going to take E, that vector of residuals, transpose times E, which in this particular case can be written as you see here. And now we want to distribute and do some matrix arithmetic, the kind that we may have seen in a linear algebra course. I do want you to note that as you expand this out using FOIL, really, we get B transpose X transpose Y, and we get Y transpose X times B. Convince yourself that those are both 1 by 1 results. Therefore, they're scalars, so they are indeed the same number. So we can combine those two things together, and we're left with the sum of the E sub I squared. That is, the sum of the squared error can be written as Y transpose Y times, minus 2B transpose X transpose Y plus B transpose X times B. Now, we're going to take the derivative of that with respect to B and set that equal to 0. And when you do that, the result is as you see at the bottom of this slide. This column vector B, which in the simple linear regression model is a 2 by 1, can be found as written here, and that gives us our estimated regression coefficients. Now, the important thing is that we have to remember that not every square matrix, which X transpose X would be, not every square matrix has an inverse. In the simple linear regression model, this isn't a problem at all because we only have one regressor, and we're guaranteed that X transpose times X is going to have an inverse. But when we get the multiple linear regression, where we have a number of different X variables, we're going to have to be very cautious about making sure that those variables are linearly independent. Because if they aren't, then X transpose times X will not have an inverse. More to say about that later. If we want to find, so we have a way to find our estimated regression coefficients, our B0 and B1. And now if we want to find the fitted value for a particular level of X, we simply need to perform the matrix arithmetic that you see on this slide. We'll take XH, where the X sub H here represents the particular value of our regressor variable, and we'll take XH transpose, so that this then would become a 1 by 2 if we transposed it. And then we have our vector B, which is a 2 by 1. So when we do this arithmetic, it's obvious, I hope, that we get a 1 by 1. That is, we get the fitted value associated with the x sub h level of x. Now, if we want the fitted values for all of the data that we have used in constructing our model, we would simply take the matrix of data, remember the column of ones, and multiply it by b. And since b is, as we have discussed, x transpose x inverse times x transpose times y, we have this result, that y hat, that is the fitted values corresponding to the data that we have, can be written as h times y. Now, at this point, it's not critical that we dissect this, but this matrix H, we call it the hat matrix, will be very important to us as we discuss analyzing the regression models that we develop later in this course and in the follow-on 431 course. The end residuals can be written in a number of different ways. One way is I minus H, where I is the identity matrix times Y. And we have to keep in mind what H this hat matrix is, and we'll discover that this plays a critical role in model analysis and residual analysis associated with our model, that is validating our model, when we get to that later in this course or in the 431 course. Now, one thing I want you to note is that these estimated regression coefficients, B0 and B1 in the simple linear regression model, they are indeed unbiased estimators. That is, the expected value of the column vector B is this vector beta, this 2 by 1 column vector beta. And you can see that arithmetic as it plays out. And as you follow this, notice that x transpose x inverse times x transpose x, that yields the identity matrix. And of course, the expected value of the error terms is 0. That's an assumption that we made. So this last term here goes away. This combines to the identity, and we've got the identity matrix times beta, which results in beta. So we've proven that the expected value of our estimated regression coefficients equals the parameters that we're trying to estimate, and that is the definition of unbiasedness. Similarly, we may want to compute the variance of these estimated regression coefficients. Remember, B in this case is a vector. It is the vector B0, B1. And it turns out that the variance of that vector can be written, and I'll just ask you to follow through the steps here. They're pretty straightforward. One thing you do want to keep in mind, and those of you who can recall this from your linear algebra course, know that if W equals some matrix A times Y, then to find a variance, we take that matrix of coefficients and we have to square it. And the way you square things using matrix arithmetic is to take that thing times its transpose. That'll do the trick. So we know that the variance of B is this matrix. We call it the variance covariance matrix of B. Now again, that inverse has to exist. In a simple linear regression model, no problem, because we only have one column of x values. We got the ones in the first column and we got the x values in the second column. But in multiple linear regression models where we have a number of different regressor variables, then we have to make sure that those variables are linearly independent. Again, more to say about that as we make our way through this course and its follow-on. Oh, one thing I forgot to mention is it's very rare that we would know sigma squared. That is, the variance that we assume for each level of x is generally unattainable unless we have the entire population. If we have the entire population, then we don't need statistics at all. So we have to find an estimate for sigma squared, and as we have seen before, a fantastic estimate for sigma squared is mean squared error. In fact, we've demonstrated that mean squared error is not only a great estimate for sigma squared, but it is an unbiased estimator of sigma squared. So our estimated variance covariance matrix is, as you see here, we make the substitution mean squared error for sigma squared. Now what about predictions? In Chapter 2, you'll recall we developed some results for predicting the mean response and predicting a new response for a particular level of x. The following results, of course, then, we don't necessarily need to have them to analyze our simple linear regression model, but when we get the multiple linear regression model using a matrix approach is going to be very, very much more efficient, and we'll certainly want to be able to do that then. Recall a particular fitted response. We take the value of x that we're interested in. We write it as a column vector. Remember the notion of the 1 is the multiplier for b0. That gives us our intercept term. And then we take the value of x and hit it by the slope, which is estimated by b1. In order to do that mathematically using matrix notation, we have to take the transpose of x sub h. That then becomes a 1 by 2 x transpose sub h. X sub h transpose rather becomes a 1 by 2. The vector b is a 2 by 1. A 1 by 2 times a 2 by 1 gives us a 1 by 1. That's the fitted value at that particular level of x. So a point estimate for the mean response at some level of x is easy to find. We just do the normal kinds of things. We hit b0 by 1, we hit the value of x by b1, we add them together, and we get our fitted value, in this case denoted y sub h hat. But it's very important to recognize that the vector of estimators is a random vector. If we had different data, then we might get different estimates for b0 and b1. And so in my opinion, having a point estimate for a particular level of x based on these point estimators b0 and b1 is troublesome, because those estimators b0 and b1, they have variation. In fact, we saw that the variance covariance matrix and the estimated variance covariance matrix associated with that vector b is, as we derived and showed on a previous slide. It's very important. I think it's critically important for you to understand that these point estimators and the point estimates that we derive using them are subject to variability. And because of that, I'm a huge fan of confidence interval estimates. And in order to generate, let me go back one slide. In order to generate a confidence interval estimate for the mean response, we have to find the variance of that point estimate y sub h hat, which can be written as x sub h transpose times b. We can find the variance of the expression that you see here, remembering that b is x transpose x times, x transpose x inverse times x transpose times y. So we substitute that in for b. We do our arithmetic. We again allude to the fact that if we're finding variance, we have to square these constants. In order to square constants in matrix, using matrix algebra, we take the matrices and we multiply it by its transpose. That effectively is taking things and squaring them. And so we follow this through, and I would ask you to do that. And eventually we arrive at this sort of horrendous looking expression for the variance of y sub h hat. Again, we don't know sigma squared. It's almost impossible for us to know sigma squared. The only way that we can know sigma squared, that is the variance at these various levels of x, is to have all the entire population. And again, if we have that, then there's no need for us to worry too much about statistics, because we can just do the analysis of the population straight away. So once again, we substitute mean squared error for sigma squared, because mean squared error is a great estimator of sigma squared. And we're left with our normal stuff when it comes to confidence intervals. If we want to find a confidence interval estimate that corresponds to a particular level of x, we take the point estimate and we add and subtract some stuff to it. Now, the stuff that we add and subtract to it includes the level of confidence that we want to have, and that is associated with the alpha level that we choose, and variation. And the variation in this case is a kind of a complex computation, but when you get into it, it's just arithmetic. And so it's nothing really to be overly worried about. We can do the arithmetic necessary to compute the standard error of y sub h hat. And it's just this computation right here. Now, and we'll do that in a moment. Now, if we want to predict a interval estimate for a particular response, notice, not the mean response, but a particular response, then we have an additional source of error. Here's a question for you. What's easier to do? Predict a mean response or predict a particular response? And of course, I'm hoping that you're able to say, hands down, that predicting a mean response is simpler. And the reason that predicting a mean response is simpler is because mean responses have less variation. Remember the mean, the variance of the sample mean x bar? It's the variance of the population that you're sampling from divided by n. And so we see that it's certainly simpler to compute a mean to come up with an estimate for a mean response than it is to come up for an estimate for a particular response. And as you'll see as you read through your textbook, we have to have this additional source of error, this additional mean squared error, if we are trying to predict a particular response. Well, I've done a lot of talking here. Let's look at an example. The file gpa-data.xlsx we've already worked with. We know that it's a sample of 20 students who took an admissions exam, and then we looked at their grade point averages later on after they had been admitted. And we want to construct a simple linear regression model to predict a freshman's GPA using the admissions exam scores as a predictor variable. We've already worked through this problem, and now we want to do it using matrix arithmetic. We want to find a 95% confidence interval estimate for the mean grade point average for students scoring 5 on the exam. And then we want to find a prediction interval for the grade point average of a particular student who has an exam score of 5. Now again, the second challenge here is a lot more difficult than the first challenge. And the reason is because variation, when we're talking about means, gets smoothed. Well, let's go to our Excel spreadsheet. This is included in fact, we've already seen it. So you can call this Excel workbook up. It's called GPA Exam Matrix Ops, and it's posted in the lesson section of our book. So you can see it, and we've gone through this before. Here's X transpose X inverse, here's X transpose times Y, etc., etc., and here's our estimates for B0 and B1 in this 2x1 matrix called B. B0, B1. And what we want to do in this particular case is we want to build a confidence interval estimate associated with a student who scores a 5 on the admissions test. So X sub h in this case, remember the 1, we need the 1 because of the intercept term. And here's the value of X. X sub h in this case is 5. X sub h transpose excuse me, x sub h then is 1, 5. X sub h transpose is the vector 1, 5, which is a 1 by 2 in this case. X transpose times x inverse. We can find that easy enough. Look, take your time and go through the formulas that I've used to create these results. Y hat in this case, if we take our 1, 5 and multiply it by our B0 and B1, which in this case can be found back here in yellow. The minus 1.69 is the intercept term, the 0.8399 is the slope. If we do that arithmetic, the y hat, the estimate, the point estimate, is a 2.5 GPA. And of course we know that has some variation associated with it. And we want to compute that variance and find its standard deviation. And so we go through the arithmetic of finding mean squared error times x sub h transpose times x transpose x inverse times x sub h. That turns out to be this value. We take the square root of it. Again, follow through all the formulas that you see here. And finally, we need to find the t-value associated with a 95% confidence interval, and we can use the t-inverse function in Excel. Again, go to the toolbar to do that, where we have n minus 2, in this case 20 minus 2 or 18 degrees of freedom. That value turns out to be a 2.1. So we take our y hat, which is our 2.5, and we add and subtract the stuff to it, where the stuff is the level of confidence and the did I make a mistake here? No. Keep in mind, the notation's a little tricky here. I'm talking about t sub 0.025, that's alpha over 2. In order to compute t sub 0.025 with 18 degrees of freedom, notice up here that the t inverse function needs to know what area is in both tails. So that's why you have the 0.05. Again, the t inverse function works differently than the norm inverse function, works differently than the chi inverse function in Excel. So don't get confused by that, but do, buckle down and go to the help menu if you have to in Excel to understand how the t inverse function works. It caught my eye, and I just wanted to share that with you. So we do the arithmetic. We subtract from 2.5 the 2.100, which is the t-value, times the 0.0972, which is the standard error of the estimate in this case. And then we add it. Notice the 95% confidence interval. We have a point estimate then for y hat of 2.5, but we're 95% confident that for someone who scored, that the mean response for students who score a 5 on the admissions test is going to be somewhere between 2.29, 2.30 basically, and 2.70. Now, what about if Len Kelly comes in and he scores a 5 on the admissions test? What can we predict that his grade point average at the end of his freshman year is going to be? Well, it's the same point estimate. We plug the value, 5 for my exam score in, and I get a 2.5 GPA. But now, because we're trying to estimate my particular grade point average, we know that has to be more difficult than predicting the mean of everyone who scored a 5, the mean GPA of everyone who scored a 5 on the admissions exam. And indeed, we add this additional mean squared error. We take the square root of that, and we get a larger value. And the upshot, you can see, if we take our 2.5 and add and subtract now our confidence, our error term, we get a lot wider interval. So we can say we're 95% confident that Len Kelly, who scored a 5 on his admissions exams, GPA will be between 1.56 and 3.43. Now that's pretty wide. And the reason it's wide is because it's difficult to predict what some particular individual's grade point average is going to be. Now, what's the conclusion? The conclusion is, look, we can do this simple linear regression problem without using matrix algebra. The intent is not to do simple linear regression models using matrix algebra. The intent is to do multiple linear regression models using matrix algebra. And so it's important that we understand and be able to make our way through the arithmetic associated with, this endeavor. And so I would ask you to spend some time looking at the results. Obviously, read the textbook. Look at the results given in the examples in our textbook. Go over the spreadsheet that I provided to you in this particular illustration, this particular lesson. And make sure you know where the formulas are coming from and how they've been derived and applied. And then take a look at the suggested homework problems and make sure that you can make your way through them. This is fundamental. We need to know and be confident with using these matrix results in order to efficiently analyze multiple linear regression models when we get to that in our next lesson.